Hello, 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 everyone. How is everyone doing? Welcome on this Monday. It is a very wet Monday in Cape Town. Thank you so much for you guys with your patience today. And I have to say a huge thank you to the moderator, Umkwebi, for ducking in at 10 and telling you guys that it was supposed to go on the newsletter, that we moved the lesson to 4 o'clock so that I can see you. And thank you for everybody for coming. Okay, I know some of the other guys are in maths lit, but that's fine, we'll deal. Oh, I've got a puppy shouting. All right, sorry about that, guys. Puppy has been taken care of. Okay, so today we're going to do redox reactions. All right. In the Oxford Successful, it's on page 192. I couldn't find it on the Study and Master, and I couldn't find it in Doc Scienza, and I couldn't find it in Platinum. So you guys know the drill. Pop it in the chat. I will write it down. I have my trusty piece of pen and paper ready. So if you can see it in any of your textbooks, let me know. It's close to where we were last week, guys. No, Braden, technically speaking, you can't. All right, so guys, as you go through, just remember to put me the pages in the chat, please, so that I can update the slides and update them going in. Just on that point, please make sure that you have gone into the Google Drive. I have updated last week Thursday slides for you guys. Remember, I promised that I'd make the table more logical. I have done so. All right, so let's get going with today's work. All right, so a reminder, we have two types of reactions. We have ion exchange reactions, which is when ions change position. We did that last week. And then we have oxidation reduction reactions. For short, we call them redox reactions. And this is when electrons are transferred from one element or ion to the other. All right? Now, new words. Oh, thank you, Kamal. So guys, study and master. I see the Google Drive pull request. So study and master is on page 225. I will update that. I see the Google Drive request. Whoops. I'm getting the Google Drive ready. We're going to get there in a moment. I promise. Okay. So when we have a redox reaction, it is a reaction in which there is a transfer of electrons. Dit is 'n reduksie oksidasie, dis 'n redox reaksie. Okay, it's a redox reaction. Now, in redox reactions, we have to have two things, right? We have to have reduction and we have to have oxidation. We cannot have the one without the other. And there goes the link for the drive too. Okay. So now we have to make sure we know what is oxidation and what is reduction. Okay. So oxidation is the process whereby a reactant loses electrons. Okay. So I have some or other something and it gives up electrons. So it becomes more positive. Right? Easy peasy, guys. So if oxidation is the loss of electrons, then reduction has to be the gain of electrons. Okay, the one cannot happen without the other. Right. Now I can already hear everybody complaining, ma'am, how on earth are we supposed to remember the difference? Well, lucky for you, I have a rhyme. It is called oil rig. Oil rig. Oxidation is loss of electrons and reduction is gain of electrons. Easy peasy, hey guys. Oxidation is loss, reduction is gain. Come on, it doesn't get any easier than that. Oil rig. Makkelijk, makkelijk. All right. So let's look at a reaction and let's see how all the parts of redox reactions of oxidation and reduction squeeze together. So I have a piece of zinc metal and I put it in a solution of copper sulfate. See, zinc is a solid, so I've got zinc metal. I've got copper sulfate in solution, aqueous, and then it forms zinc sulfate, which will be in solution, aqueous, and copper metal, solid. Okay, so let's look at how this happens. Thanks, Pops. Right. Let's look at how this reaction happens. Now, you guys will remember from last week, we have the whole reaction, the total reaction. Then we break it down into its ions, and then we chuck away the spectator ions, the things that are not actually doing anything. Okay, so we're going to use this reaction and those concepts from last week to separate this reaction into an oxidation and a reduction reaction. Okay, right. The net reaction for this thing. Can you see that the sulfate ion here on the left is also on the right? Can you see that? It is a sulfate ion on the left and a sulfate ion on the right. So sulfate stayed in solution. It stayed an ion. So sulfate ends up becoming my spectator ion. So when I remove sulfate, I end up with my zinc metal over there and my copper cation over here. And here I have my zinc cation and my copper metal. Okay, guys, can you see the only difference between this total reaction and this net reaction is my sulfate ions. That's the only difference. So here's my net reaction. Let's have a look at which part of this reaction is oxidation. Larissa, you want me to go back to the previous slide just for that? Okay, so okay, it's okay, guys, it's fine. This is my total reaction. I take zinc metal, I put it in a solution of copper sulfate, and this reaction, the reactants here react, becomes zinc sulfate and copper metal. This happens to be the reaction that happens in a battery, like a Duracell battery. Okay. So, can you guys see that on the left, I have zinc, I have copper ions, and I have sulfate ions. On the right, I have zinc ions, I have sulfate ions, and I have copper metal. So you can see from the one side to the other, the sulfate ions stayed the same. They just went from being attached to the copper to being attached to the zinc. So I can view my sulfate ions as spectator ions. They don't take part in the reaction. They are sitting on the bench. They don't take part in the reaction. They're just watching. So it's easier to work with the net reaction. The things that actually react. The things that make this an redox reaction. Sulfate doesn't make this a redox reaction. I hear you. I think I'm going to add a step in for you, Larissa. Let's just get a Mimeo going. Okay. Let's do it this way, guys. Don't panic. Oh, clearly. All right. So we started with copper metal. No, we didn't. No, we didn't. Okay. We started with zinc metal and copper sulfate solution. And that formed zinc sulfate solution and copper metal. Sorry guys, my puppies have decided they want to be loud today. Okay. Now last week we said we can write some of this in iron form. Okay. So we can say, well, zinc is still a metal. It's not an iron. There's nothing much we can do about that. But copper sulfate, we can write as copper ions plus sulfate ions. And zinc sulfate, we can write as zinc ions and sulfate ions. And copper is just copper. Okay. I'm just quickly going to erase that state symbol. It doesn't make sense to have it there. Okay. Now, so this top one is the total reaction. And this one is the ionic reaction. So the top one is the total or the complete reaction. The second one here is what we call the ionic reaction. Because remember, we split everything into its ions. Now I find the spectator ions, the ions that are the same on the left and the right. And the only one that is the same is that sulfate. Now, I know a lot of you want to go, but ma'am, there's a zinc and there's a zinc. But remember, when it's a metal, it has a charge of 0 And on this side, it has a charge of +2. Same thing. On this side, copper has a charge of +2. And on this side, it has a charge of 0. Okay. So the only thing in this reaction that I can consider a spectator ion, sorry guys, is sulfate. So what I do is I say, well, the spectator ions are not players on the field. So I ignore them. They are not playing the game, they're only watching. Now I write down all the guys that are actually playing on the field. And that reaction is called my net reaction. Is that better? Are we less confused? Ashley says no. Anyone with Ashley? How do we know it's charge? Okay. Poppy says better. Guys, are you actually more struggling with the fact that there's a charge there? I have a feeling that might actually be it. Okay. So to answer Braden's question, I know. To answer Braden's question, Braden, sulfate always has a charge of -2. It's a fact. It's something you have to go and learn. I'm sorry, I can't do you better than that. Okay? Sulfate always has a charge of -2. And they give us this top reaction. They say to us that zinc metal and copper sulfate forms zinc sulfate and copper metal. Okay? And remember that charge there plus that charge there must give me 0 because there's no charge on this molecule. And that charge there plus that charge there must give me 0. That is how I could figure out zinc and copper's charges so that I could dump the spectator ion. I know it's hard, guys. I know it's hard. I know. Okay. Have a look here quickly. Here I have zinc metal. Nah? Here I have zinc metal. And here I have a zinc ion. What do you think happened for zinc, the metal, to become an ion? Yes, Corley, you're on the right track. I understand what you're trying to say. Poppy, you got to my question. Good girl. Zinc metal becomes zinc ion. It went from 0 to +2. So it lost electrons. Okay? Look what happens to copper. Copper started out as being an ion with a 2+ charge, and at the end of the reaction it was a metal with a 0 charge. So we've already established that zinc lost electrons. What happened to copper? Yes, Ashley. Copper gained electrons. Super. And that is the entire crux the entire crux of redox reactions. Yes, Braden, there are certain compound charges that you need to know. Something tells me I need to make you notes on that too. I will pop it in the drive. So I need to compound charges. And then Braden, I'm going to add to the Lewis diagrams how to go from a Lewis diagram to a Cooper diagram, which is only really for grade 11, but if you can understand it, it's super easy. Okay, so this seems to be feeling better now. Right, let us go back to the PowerPoint. Right, so we've established this net reaction. And we've kind of now spoken about the next two slides, okay? Zinc went from having a 0 charge to having a +2 charge. Zinc went from having a 0 charge to having a +2 charge. So it lost electrons, like Poppy said. So zinc metal was oxidized to zinc 2+ cations. Remember, guys, cations are positive and ions are negative. I'll draw those pictures for you guys too again. Okay. So zinc was oxidized oil rig. It lost electrons. But now, unfortunately, in chemistry, nothing's ever that simple. So we have to write it out slightly further. Okay. Now, in maths, what sign do we normally use if we lose something? If something gets given away? If something gets less? What mathematical sign? There we go, Miss P. Come on. Good job. We normally use minus now. Okay. Now, the problem in chemical reactions and chemical equations is that even though something gets lost from one thing, it goes to another. And so writing this whole thing out, writing a negative. Yes, Tina, you're on the right track. Chemistry is opposite. Right. Okay. Writing that zinc -2 electrons gives me zinc 2+. Makes no sense in a chemical reaction. Okay. So we write this reaction and we call it the oxidation half reaction. Why half reaction? Because it's half of the whole redox reaction. Okay? So we say that zinc becomes zinc 2+ +2 electrons. And I know that that bothers you. I get it. I get it, I get it, I get it. Okay? The metal lost 2 electrons, it became a cation. So we want to write this. I get it. Okay, we want to say zinc metal -2 electrons became zinc 2+. The problem is that although zinc metal lost 2 electrons, the entire reaction didn't lose 2 electrons. Those 2 electrons came from somewhere. They went somewhere. They did something. And so in a chemical reaction, if you feel like you want to write minus an electron on any of the sides, it's normally on the left. Then instead of writing it as -2 electrons, you take it across the equal sign and it becomes +2 electrons. Okay. So I often used to use this reaction here at the bottom. I used to say zinc metal -2 electrons. And then I would remind myself that I am not allowed to write minus in a chemical reaction. and I would take my electrons over and it becomes plus. Tino, yeah, they are a little bit, they like factorization because you're factorizing out the spectator ions, okay? And you are balancing, which is a lot like algebra. You know, what you do on the one side, you have to do on the other side. What you have on the one side, you have to have on the other side. Okay. Actually, in this week, it's coming up after this. Okay. Stoichiometry. Don't worry, Miss P. Okay. So we've dealt with the fact that we want to write the minus, but in chemistry, we can't write a minus. It doesn't make any sense. So we write it as a plus. Okay. So this was oxidation. And it's a half reaction. Tino, don't panic. I'll tell you guys tomorrow. Focus with me now. It's an oxidation half reaction because it's half of the whole reaction. Now we have to look at the other reaction. Okay? Right. Reduction is the other half. So zinc lost electrons. It was oxidized. Copper 2+ gained 2 electrons and became copper metal. So copper went from having a 2+ or a +2 charge to having a 0 charge. Okay? So it gained electrons. So anions, that's wrong. It's a cation. Oh, I'll correct that. Sorry. This is a cation, was reduced to copper metal. Okay. Now again, let's look at how that happens on a microscopic level. So this is the reduction half reaction. Okay. I had copper 2+. It gained 2 electrons and it became copper solid, copper metal. Now this one's easy, guys. Like this, we don't struggle to write this one. Okay. I'll correct that. It's a cation, gained 2 electrons, became copper metal. I don't know what was up with me last night when I typed this. Okay. So this is a logical, easy one to write. Okay. So we have had the oxidation half reaction and we've had the reduction half reaction. We know to oil rig, oxidation is loss of electron, reduction is gain of electron. So the two together, oxidation plus reduction, give me redox reactions. Okay. So when we write redox reactions, we combine our 2 reactions and we get the net redox reaction. I know, that's why I gave you the words right in the beginning with all those definitions. Okay. There are 3 super easy steps, like not even a little bit hard, that you have to follow. Okay. The first one, you write down both half reactions, one on top of the other, one above the other. You make sure you balance the electrons. So if you have 2 electrons on the left, you have to have 2 electrons on the right. Then, because the electrons are balanced, they cancel out and you have a net redox reaction. So let's do these 3 steps with the reaction we've done today. Okay. So the first thing we do is we write down both half reactions. We write down the oxidation half reaction, which is zinc metal, which becomes zinc 2+ iron plus 2 electrons. and the reduction half reaction, which is copper 2 plus, which gains 2 electrons and gives us copper metal. Now we have to balance the electrons. What does anyone think? What maths are we going to use? What we have on the left, we have to have on the right. Come on, opinions. Ms. P, are you saying yes, they are balanced? Is that what you're saying yes to? Where do you want to add 2 electrons, Kamal, and why? It's okay if you guys aren't sure. Take a stab at it. Gordley says they are balanced. Why do you say they're balanced, Gordley? Asidi says they're not. So, Gordley, tell me why you think they're balanced. Asidi, tell me why you think they're not. Ashley also says they're not. Why, guys? Come. Just because you think so or because you feel so. I don't mind if you guys say yes or no. That's not the point. I want you to see why you say so. Okay. So, guys, this zinc here, I also have here. Okay, Corley, I'm going to use your explanation. Just give me a second. Okay. This zinc here, I also have on this side. So I've got one zinc atom on this side and one zinc atom on this side. The only difference is that the zinc atom lost 2 electrons. Okay. So technically speaking, I have the same number of zinc on both sides. If I look at the bottom here, I have the same number of coppers on both sides. But on the left, copper was attached to something, so it had a +2 charge. And then from somewhere it gained 2 electrons and it became copper metal. It's just different charges, Poppy, yes. Now, when I say balance the electrons, guys, I literally mean the only thing that you check is whether or not you have the same number of electrons on the left and on the right. Let's see if I can write with a pen. On the left, no halsney. On the left, I have 2 electrons. Do you see here? Okay. On the left, I have 2 electrons. And on the right, I have 2 electrons. I know that these charges here are throwing you guys. Only look at the electrons. Only balance the electrons. Yes, Corley, exactly correct. You were exactly correct. Okay. So guys, can you see that on the left I have 2 electrons? And on the right I have 2 electrons. They're just in 2 opposite halves of the reaction. There we go. So our electrons are actually balanced. Okay. Now what we do is we say, okay, well, this electron there and that 2 electrons there, they cancel out. Okay. And so we end up with the net reaction, which is the reaction we started with anyway. They're not always this simple. They're not always 2 electrons and 2 Right. I want you guys to practice one for me. Magnesium and hydrochloric acid. Magnesium is a metal, hydrochloric acid. Remember, we did this when we did acid-base reactions. Okay? We also did this when it forms a gas, because it is a gas-forming reaction. But there is electrons that transfer. Okay. Of course you'll get them, Miss P. Okay, so here's the total reaction. From that total reaction, I want you guys to, if you can eyeball, just look at it and tell me what thing in there, what element, what ion do you think, do you feel is going to be the spectator ion? Pops, why do you say Ng? Come on, what? Oh, come on, I know why you're saying H. Okay, Brayden, what they are saying is, remember H2 is a gas, okay? Cl here is attached to H. And Cl here is attached to something else. Remember, guys, why is it Cl2? Because magnesium is in what group? What group is magnesium in? 2. And so when magnesium bonds with something, what type of charge does it make? It's got 2 valence electrons. It gives it away. So what type of charge does magnesium have when it bonds with something else? Not quite what I'm looking for, Tyler. There we go. Thanks, Ash. Tyler, I can understand where your brain was going. I didn't word my question correctly. Okay. So Ashley says that when magnesium bonds with something else, it makes +2 bonds because it is in group 2. So it has 2 electrons it needs to give away. Chlorine is in which group? 7. So when it bonds with something, what charge does it have? -1. So this +2 here needs how many chlorines? There we go, come on. And that is why there's a 2 there. It shows that for every 1 magnesium, I need 2 chlorines because of electron transfer between these 2 things. Okay, so chlorine is still an ion. It's still -1, but I need 2 of it because magnesium is +2. Don't worry, guys. I will have to tell you guys this a million times over still. It's fine. Okay, right. So Cl and Cl. No, Brayden, it doesn't matter if it's Cl2. It's only Cl2 because magnesium is +2 and chlorine is -1. Okay, so Cl here is in solution and Cl here is in solution. Okay, so guys, those of you who guessed Cl, wait, I forgot I did this. Anyway, Cl is the spectator ion. Next question is balanced. No. Okay. We have one hydrogen and one chlorine on the left. We have two chlorines and two hydrogens on the right. Luckily, it's a very, very, very easy balance. Okay, I just whack a 2 there in the front. Okay, you see that? I just need 2 of that. It's a very, very easy balance. I will go over balancing with you guys again when we do stoichiometry. Right. So now you guys ask me for the net reaction. There's my iron. There's my iron. Okay. So chlorine, because it's an iron on both sides. So I can drop chlorine on both sides. And there is my net reaction. All right. Who wants to guess? Does magnesium becomes Mg2 plus? Does magnesium get oxidized or reduced? Is it oxidation or reduction? Magnesium, oxidation or reduction? Miss P's got lots of question marks there. She's not sure. Yes, you guys. Magnesium lost electrons. Oil rig. Magnesium was oxidized, which means hydrogen was reduced. Easy peasy, nah? Okay. What is oxidation? What is reduction? Oil rig. Oil rig, oil rig. I cannot tell you guys that enough. Okay. So, oxidation, magnesium from 0 to 2 plus. So it lost electrons. So there is my oxidation reaction. Okay. Reduction is then the other side of it. Hydrogen went from +1 to 0, but be careful, there's 2 of them. 2 of them. Each hydrogen gained 1 electron. There are 2 hydrogens, and so my reduction half reaction is H plus 2H plus 2 electrons. I know, I can see, calm down. So then I do my 3 steps. Okay, I write down my oxidation, write down my reduction. I balance my electrons. Look, there's 2 and there's 2. It's already done. And so that is my redox reaction. Right. So there are 3 homework problems for you to struggle with. The first one is nickel plus iron sulfate becomes nickel sulfate plus iron. Remember, guys, sulfate, SO4, always has a charge of -2. So the first one is balanced. The second one is not balanced. Okay? And the third one I gave you in words to see if you're willing to try. Guys, we worked with silver nitrate last week. Silver almost always has a charge of +1. So you can assume that it's going to be silver +1 nitrate. Okay. Excuse me. Brayden, it's all in the drive, dude. Okay. Tyler. Guys, it really is already in the drive. Okay. So, tomorrow at 4, we will start with these 3. No? And then we're going to do stoichiometry. Deal? Okay. I will see you guys tomorrow at 4. I hope it is less cold, although I'm enjoying winter. I absolutely loved seeing you guys. You absolutely made my day. I had a really long, tough one. And tomorrow we will talk about the road going forward. Say the word slowly. Stoichiometry. Bye, family. Be good, be safe. Just bye.